This is part 4. And in the part 3, the last lecture, we discussed the rational number system. And we learned that the natural numbers were subsets of the whole numbers, which are subsets of integers, which are all subsets of the rational numbers. And then there were irrational numbers, which were numbers that weren't rational. And together, those two numbers, the union of the rational numbers and the irrational numbers, make the real number system. And all of these numbers can be plotted. And that's kind of what I want to talk a little bit more about today, to start off with, is this coordinate system. And it's kind of picky how it's drawn. I know people that use rulers and get real formal. I'm not like that. I think if you draw a close enough straight line, that's good enough. And they get real picky about the distances between these coordinates, and I think that's just a little crazy. But there is some things that we need to talk about. 0 is referred to as the origin. So 0 is referred to as the origin. And if you notice that this side doesn't have an arrow on it and this side does, that is on purpose. That is to indicate that the numbers increase from right to left. From left to right, I'm sorry, from left to right. So, and generally, the arrow is going to be on the right side. And notice later in 2 dimensions, it looks like this, where the origin is here, but I don't want to jump too far ahead. I'm just saying that a lot of people put arrows on both sides, and that's incorrect. You only put the arrow in the direction that the numbers are increasing. And points on this, let's just call this point A. We could say that A lives at 3/2, or A lives at 1.5, whichever you prefer. And you can say A is 3/2. Okay, A is 3/2. Or sometimes you could see it A like this. Sometimes this notation is good. Either one works for me. Now, what's important, I want to discuss a little bit more. I'm going to put point B here. And real numbers, and we discussed this briefly in the last lecture, but I want to go a little bit into more detail. Real numbers are ordered. And it's hard to imagine number systems that aren't ordered, but there are number systems that ordered is irrelevant, means absolutely nothing. And that's not too far from now. We will discuss one, and that's the complex number system. They're not ordered, but these numbers are ordered. Real numbers are ordered. So that means, and as I said, the arrow indicates they grow from left to right. So numbers on the left are less than numbers on the right. So we could say that 3/2 is less than 9/2. Okay? 3/2 is less than 9/2. Or you could say that 9/2 is greater than 3/2. Okay? So the larger number is to the right, and the smaller number is to the left. Okay. Another thing I want to talk about real quick, because it's not a very difficult concept, but a lot of people get confused with it later, especially when we start solving equations with this concept, and that's absolute value. Absolute value. And the absolute value is defined as these formal bars. So we can say the absolute value of a number. That's how it's notated. That's not how it's defined. It's defined to be the distance between a number and the origin. Okay. The distance between a number and the origin. So if you notice here, let's look at -2. You can see that -2 is 2 units from the origin, And positive 2 is 2 units from the origin. And one thing that's very important, and I think this is something that you should already know, is distance is always positive. So we could say that the absolute value of a number is always greater than or equal to 0. Right? It's always positive, or we're at the origin. Okay? So really what we're doing when we find this absolute value is we're stripping the number of its sign, in a sense. That's not the mathematical term for it, but that's what we're doing. Okay? So the absolute value is the distance between, so the absolute value of negative pi, okay, would be, we just strip the sign, would be positive pi. Okay. And the distance between 2 points, 2 as in the number of points, the distance between 2 points in one dimension and the distance between 2 points, A, we'll just call these A, lowercase a, and B. So the distance between 2 points A and B in one dimension, now this formula only works for one dimension, is defined as the absolute value of their distance, the difference. Okay, so this is defined to be the absolute value of their difference. So, and maybe it's not so noticeable that the distance between 3 and 5 is 2, and the absolute value of 5 minus 3 is 2, right? But what may not be so noticeable, what's the distance between 5 and negative 4? Well, the absolute value of 5 and negative 4 is, well, when we subtract a negative, we add, is the absolute value of 9, which is 9, and you can count from 5 to 1, 2, 3, 4, 5, 6, 7, 8, 9, and it works. Okay. And one important thing to notice is that it doesn't matter which one you subtract. The absolute value of A minus B is equal to the absolute value of B minus A. Okay. Okay, so that's absolute value. Now we're going to move on to the next topic, and we're going to talk about some properties of addition and multiplication. And these usually aren't very exciting. I don't really want to call them properties. I want to call them like tips to help you carry out some operations in math. Okay, so the first property is what we call the commutative law. The commutative law, and it applies to addition and multiplication, both. All right, and it's based on this word commute here. To commute is to go back and forth. So when you're adding, or only multiplying, the order which you do this is irrelevant. Kind of like the absolute value thing we just did. But that's absolute value is not commutative. But this is A plus B is equal to B plus A. And 3 plus 4 is equal to 4 plus 3. That would be an example with numbers. A times B is equal to B times A. 3 times 4 is equal to 4 times 3, and etc. Okay? That is the commutative law. The next law is a lot more helpful, Associative Law. And it involves only adding, or only multiplying 3 or more numbers. And what it basically says is when performing only addition or only multiplication on 3 or more numbers. So when performing only addition or only multiplication on 3 or more numbers, it doesn't matter which pair you add first. That's kind of how you say it in English. And I'm going to show it in math language, but add or multiply first. Okay. It doesn't matter which pair you add or multiply first. So let me show you an example, or let me show you the property. Let me do it down here so it's underneath the Associative Law. So if we're adding 3 numbers, but just keep in mind this applies to 12 numbers, it applies to a billion numbers. If we add these 2 numbers first, we get the same result as if we add these 2 numbers first. And if we're multiplying A times B times C, that's equal to A times B times C. If we multiply these 2 numbers first, it's the same as multiplying these 2 numbers first. And how does this property? This property is actually very helpful. Let me give you an example of addition. Okay. This is all only addition. Now, if you go from left to right, it's a little more difficult than it is if you do what I'm going to show you. But you could go 4 plus 7 is 11, 11 plus 6 is 17, and 17 plus 3 is 20. Or you can add 4 and 6 first and see that that adds up to 10. And you can add 7 and 3 and see that that adds up to 10. So this is 10, and this is 10, and you get 20 either way. Okay? So sometimes when you look for patterns that end in 10, when you're adding multiple numbers, it makes things easier to add. What about multiply? 3 times 5. How about 13 times 5 times 2? Okay. Now, some of you might not know that 13 times 5 is 65, and 65 times 2 is 130. But if you see that 5 times 2 is 10, and it's easy to multiply by 10, 10 times 13 is 130. So if you multiply these 2 first, it's a lot easier than going from left to right. Okay? In fact, you could do this before you even pick up the calculator, if you do it in your head, right? 5 times 2 is 10, and you just put a 0 on the end of 13. I mean, you should, sometimes doing it this way is faster than picking up a calculator. Okay, we have one more law property we're going to look at, and it applies to addition and subtraction and multiplication, and it is called the Distributive Law. To distribute something, if I was in a class and I had 12 students and I distributed something, that means I gave all 12 students the same thing. That's distributing. Okay? So what the Distributive Law says is if I take number A, we'll just say A, B, C, and D are real numbers. Okay? So if I take a number A and I multiply it by B plus C, I can distribute over multiplication. That means A times B, so this is equal to A times B plus A times C. So the A is distributed over this sum. And it also works for subtraction. Now you're going to see me do this in the future. Instead of writing it out twice, if I say it works for subtraction too, you just put a minus under it like that, plus or minus. So what this is saying is that A times B plus C is true, and A times B minus, B minus C is true. So this would be A plus AC, and it applies to subtraction as well. Okay, so instead of writing it twice, I just put a minus there. Okay, that means it works for minus also. All right, so where does this come in handy? Well, one, you wouldn't be able to multiply 32 times 25 without the distributive law. Okay, because really what you're doing is you're multiplying 32 times 20 plus 5. Okay, this is what you're really doing when you multiply this out. Because the first thing you do is 32 times 5, and that's going to be what? 160. And then you're going to do 32 times 20, which is 640. And then you're going to add them up, right? Which is just the same thing as this, right? You're doing the distributive law. Your brain might not be trained to realize that that's what it is. And you add it up and you get, 800? Okay. Some people use this trick as a way to do some simple math in their head also. Some people know that 32 times 2 is 640, and you can add 160 to 640 in your head, and that's just kind of a little trick. We're going to use the distributive law a lot when we start multiplying algebraic expressions. You betcha that's going to come up. Okay, so that's where we're going to see this again and again and again and again. And that's going to conclude part 4. I appreciate you watching. This is still all part of problem set 1, and we'll continue next time. Thank you.